Albert Einstein's contributions to science are vast, but one of his most groundbreaking discoveries, and the one that won him the Nobel Prize in Physics in 1921, was his explanation of the photoelectric effect. While the idea of light was already well studied before Einstein, his work on this phenomenon fundamentally changed how we understand light and energy. This concept laid the foundation for quantum mechanics and influenced everything from our understanding of atomic physics to the technology we use in our everyday lives. What was the theory before Einstein's work? In the late 19th century, the scientific community widely accepted the theory that light behaved as a wave. This wave model was able to explain a variety of phenomena such as refraction, where light bends as it passes through different materials, and diffraction, where light waves spread out or interfere when they encounter obstacles. This model, developed by scientists like James Clerk Maxwell, provided a framework that seemed to answer many questions about light's behavior. But there was a mystery that wave theory couldn't explain: the photoelectric effect. The photoelectric effect was first observed in 1887 by Heinrich Hertz, a German physicist known for discovering electromagnetic waves. Hertz noticed that when he shone ultraviolet light onto a metal surface, it caused the metal to emit electrons, creating an electric current. This was a strange result because, according to wave theory, the energy of light should depend on its intensity. So, a brighter light should transfer more energy and emit more electrons with greater force. However, the experiments showed something else entirely. The brightness, or intensity, of the light didn't affect the energy of the emitted electrons. Instead, what mattered was the color, or frequency, of the light itself. For example, no matter how bright a beam of red light was, it wouldn't cause any electrons to be emitted from certain metals. But even a dim ultraviolet light could immediately knock electrons out of the same metals. This phenomenon was puzzling because, in wave theory, energy is spread out continuously, and a brighter light should theoretically have more energy to knock out electrons. Scientists couldn't explain why the frequency of light, not its intensity, seemed to determine whether electrons were ejected. This is where Einstein's genius came in. In 1905, Einstein proposed a radical solution to this problem in a paper titled On a Heuristic Viewpoint Concerning the Production and Transformation of Light. He suggested that light doesn't just behave as a wave but also as a particle. According to Einstein, light is made up of discrete packets of energy, which he called quantum, but which are now known as photons. Each photon, he said, carries an amount of energy proportional to the frequency of the light. This idea was groundbreaking because it contradicted the traditional wave theory of light, suggesting instead that light has a dual nature. It can behave both as a wave and as a particle, depending on the circumstances. Einstein's theory suggested that when light shines on a metal, each photon carries energy that can be transferred to a single electron. If the photon has enough energy, it will knock the electron out of the metal, resulting in the photoelectric effect. The key here is that the energy of each photon depends on the frequency of the light. Higher frequency light, such as ultraviolet, has more energy per photon than lower frequency light, such as red light. Therefore, ultraviolet light can knock electrons out of the metal even at low intensity, while red light cannot, no matter how intense. This proposal by Einstein explained several mysteries about the photoelectric effect. Firstly, it explained why there is a threshold frequency, below which no electrons are emitted, regardless of the light's intensity. If the frequency is too low, the photons don't have enough energy to dislodge electrons from the metal. Only photons with a frequency above this threshold have the required energy, which is determined by the metal's work function, the minimum energy needed to eject an electron from its surface. Secondly, Einstein's theory clarified why increasing the intensity of the light only increases the number of emitted electrons, not their energy. In the particle model, the number of photons increases with intensity, meaning more photons are hitting the metal's surface, causing more electrons to be ejected. However, since each photon transfers only its own energy to an electron, the energy of individual electrons depends solely on the frequency of the light, not the number of photons. Finally, Einstein's theory resolved the issue of instantaneous emission. In wave theory, scientists had expected a delay in the ejection of electrons, as they thought the metal would need time to absorb enough energy to emit an electron. But experiments showed that electrons were emitted immediately as soon as the light hit the surface. In Einstein's photon model, each photon transfers its energy to an electron instantly, which accounts for this immediate effect. Einstein's explanation of the photoelectric effect was revolutionary, because it introduced the concept of quantized light and confirmed that light could behave as both a wave and a particle, a concept known as wave-particle duality. This idea laid the groundwork for quantum mechanics, the branch of physics that studies the behavior of particles on an atomic and subatomic level. At first, Einstein's theory was met with skepticism. Many scientists were hesitant to accept that light could be both a wave and a particle. However, experimental validation came in 1916 when physicist Robert Millikan conducted a series of precise experiments on the theory. Millikan's experiments showed that the kinetic energy of the emitted electrons correlates with the frequency of light, not its intensity. This confirmation not only validated Einstein's theory, but also helped solidify the concept of photons as real, measurable entities. With Millikan's confirmation, Einstein's theory gained acceptance, and in 1921, he was awarded the Nobel Prize in Physics. Not for his work on relativity, as one might expect, but for his explanation of the photoelectric effect. This work was considered one of the earliest and most compelling pieces of evidence for quantum mechanics. The implications of Einstein's discovery went far beyond the photoelectric effect itself. His idea of quantized light led to a new understanding of energy and matter at small scales, paving the way for quantum mechanics and profoundly influencing physics in the 20th century. Quantum mechanics would go on to explain a wide range of phenomena that classical physics could not, including atomic structure, chemical reactions, and the behavior of electrons in materials. Moreover, Einstein's work on the photoelectric effect has had a significant impact on modern technology. The principles of the photoelectric effect are the foundation for photovoltaic cells, which convert sunlight directly into electricity. This technology is at the heart of solar panels, which have become essential for sustainable energy production worldwide. Other applications include photoelectric sensors, which are used in everything from automatic doors to light-sensitive devices and cameras. The photoelectric effect is also crucial in medical and scientific imaging technologies, where it helps detect light and convert it into electrical signals for analysis. In conclusion, Einstein's work on the photoelectric effect transformed our understanding of light and introduced the world to the strange and fascinating realm of quantum mechanics. His insight that light could behave as both a particle and a wave was a groundbreaking concept that challenged classical physics and opened up new avenues of research that continue to influence science and technology to this day. Einstein's explanation of the photoelectric effect remains one of the most significant achievements in physics. Follow for more stories that delve into the fascinating discoveries of science.